Hi, in this video we will talk about gradients and how to use them to find edges or orientation in images. When we try to identify objects in an image, finding its edges is one of the most informative methods. In a previous video we mentioned that an edge usually creates a difference in the pixel values. Specifically, in a grayscale image, we might find sharp changes in brightness. However, we also need to take into account that not only edges can cause those changes. For example, dramatic changes in albedo, surface orientation, and illumination can also result in a dramatic change of brightness. Therefore, depending on the scene, we need to put attention on those other possible causes. Calculating the image gradient can be a useful way to get those differences. The image gradient is calculated as the derivative of the image with respect of each of the image dimensions. Because our image is discrete, we can then use the finite difference, or in other words, the difference between each pixel and the previous one in the same dimension. However, this simple finite difference have a problem. As we discussed in a previous video, noise can have a deep impact on pixel values and therefore in the gradient. So one way to reduce this problem is to smooth the image before calculating the gradient. Let's look at these examples. This is the original image. Then the second one has a small amount of noise. And the third one is a little bit more noisy. Now, here are the finite difference in the x direction. It is evident that the lines in the last one are less clear than in the original. However, if we apply a Gaussian smoothing before calculating the gradient, we can see an improvement, especially in the image with more noise. Here, instead of doing two operations, the smoothing and the differentiating, we can combine these two in one convolution. The finite difference is also linear and shift invariant, so there is a kernel that can perform this operation. And because convolution is associative, we can write this expression that tells us that we need only convolve the derivative of the Gaussian, instead of first smoothing and then get the difference. Remember that filters looks like the effect that they are intended to detect. The x derivative of a Gaussian filter looked like this. The choice of sigma used in estimating the derivative is often called the scale of the smoothing. This scale has a substantial effect in the response of the derivative filter. For example, if we apply a filter with a scale of 1 pixel, we will obtain this. If we increase the sigma to 2 pixels, we can see that the resulted image has thicker lines but also lose some detail. Therefore, the selection of the sigma will depend on the image and what we want to find. We can calculate the magnitude and the orientation of the gradient on each pixel. When we are computing the gradient in both x and y, the magnitude can be calculated as the square root of the sum of both derivatives squared, and the angle as the arctangent of the y derivative over the x derivative. The gradient magnitude is already a good approximation to an edge detector. Here you can see that the scale of the smoothing also has an impact on the thickness of the resulting lines. In this particular example, the gradient magnitude of the first image looks accurate, but the line is broken in certain areas. The gradient magnitude with a larger smoothing has more continuous lines, but those lines are really thick to be used as an edge. In both cases, the value of the magnitude changes over the image. To solve this problem, we can use a technique called non-maximum suppression. We can see the lines in the magnitude image as hills, so we want to find the path that goes on the top of each hill, regardless of the height of the hill. In other words, we want to find the local maxima of each path and remove all the other pixels. The procedure is straightforward. First, we create an empty image of the same size of the magnitude image. Then we loop over the magnitude image and check the gradient orientation of the current pixel. Depending on this value, we compare the current location with the pixels that are perpendicular to the gradient orientation. If the current pixel has the highest value, then we write this value on the new image. If this is not the case, then we write 0 and we continue. The non-maximum suppression will identify pixels that are higher value on each path. The resulting image still has different magnitude values on different lines. Here we need to define certain criterion to remove those lines that are not relevant. At this point, different approaches can be taken to improve the detection. Let's say that we select a threshold and we classify our pixels into strong and weak. With hysteresis, we're going to check each of the weak pixels. And if the current location is surrounded by a strong pixel, then it will become also strong. This will convert those pixels that had a lower magnitude value, but that they were close to or part of a strong line. Finally, we remove the remaining weak pixels, and this whole procedure is called the Canny edge detector. This is a popular algorithm that can give good results. But if you start to use it, you will find out that it can be challenging to always get the edge that you're looking for, especially in real-life images. Okay, in this video we learn about image gradients. We review the process of an edge detector and that many alternatives can be implemented to improve this task. See you in the next video.